Hello everyone, how you going? Welcome to another one of the university, Monash University's School of Earth, Atmosphere and Environment, one of our high school lessons. And today we're going to be looking at climate science. And in particular, we're going to focus on the difference between weather and climate. And this is really important because often when we hear politicians or some members of the general public, or we hear business leaders or anyone really, and they start to talk about climate science, they often can use an analogue of, well, it was really cold last week in my particular hometown, so therefore climate change isn't happening. So what we need to do is understand the difference between weather and climate in order for us to try and explain the science of climate change to people in general. So that's what we're going to be doing today, the difference between weather and climate. And as I say here, my name is James Dricoll. I'm one of the assistant lecturers here at Monash University. And that's, as I've got here, this is kind of something which gets mentioned quite a lot, especially when people are trying to say that climate change isn't happening. So that's why this is important, this particular lesson. So the first thing we can do is there's a couple of really cool sites that we can go to, and that is looking at weather. And weather is basically what's happening in the Earth's atmosphere at any given time. And weather has many variables. We have temperature, precipitation, humidity and wind, and cloud cover and sunshine. All of these elements make up our weather. Sometimes it can be warm, sometimes it can be cool, and when it changes day by day, what we're doing is we're looking at how weather changes. Now, there's a couple of really good sites that we can use. The first one is this earth.nullschool. What this is an excellent site which shows you semi-real time what's happening in our atmosphere. This is taken today on the 22nd of April. And this is when I'm recording this. So I took this screen snap a couple of hours ago, and I also looked at the Bureau of Meteorology's weather site, and I downloaded this particular map. This is showing you what the forecast weather is going to be for the next 48 hours here in Australia. Now, a couple of things to point out. First of all, these lines coming through here, we call those isobars, and those isobars join together areas of equal pressure. So when those isobars are nice and close together, it means there's a high pressure gradient across this area, which means it's typically very windy. However, when we get nice big high pressure systems like here with very few isobars, this kind of tells us that we're going to get quite less windy or still conditions. And we can see that quite nicely on the Null School website, because most of Australia, apart from these two low pressure systems down here, these indicating there's really, really high winds within these two systems. And there's also a lot of wind going through here in Tasmania. When we look there, you can see that quite nicely. We've got a low pressure system here. The isobars are quite close together, so we're going to have rain in parts of South Australia and Western Victoria and Tasmania. Be fast forward to tomorrow, you can see that this second system here, which is this system here, is starting to come up towards Australia as well. So that first system, which is just here, is brushing through the Great Australian Bight here. So this is kind of telling us about weather. This is what we're experiencing today and tomorrow. This is weather. Oops. Let's get that working. Okay, so I've got actually a pretty cool YouTube clip here. This is basically showing the Earth's what happened in Earth's weather over the last year, so in 2019. It goes all the way from January to December. This is based on work from the European satellites, also American and Canadian satellites, and Japanese satellites. And all that information is put together by the group who made this video. And it's showing you how weather patterns change day by day over the entire Earth, which is pretty cool. It's quite nice to watch this. A few things to point out. First of all, this is January, just down here, because it's January. This is the Northern Hemisphere, and so much of the Northern Hemisphere is covered with snow because, of course, it's winter up there. Very little snow in the Southern Hemisphere because, of course, we're in our summer, apart from Antarctica down here, which still is in summer, but it's pretty cold, so that's why we get ice and snow all year round down there. So if we just fast forward this a little bit, we can see we're going into March. Snow cover is beginning to decrease here, and so a lot of the snow is melting because it's coming into spring in the Northern Hemisphere. And by the time we get to May, for instance, you can see that snow line has moved very far north here. Now, one thing which is pretty cool about this is 2019, and 2019 is when we had a particularly devastating hurricane in the Caribbean. And if I fast forward it to about there, I want you to just check this little patch of this low pressure system here, which will grow, as you'll see when the name comes up, into a particularly devastating hurricane, which is Dorian. So Dorian's moving through the Caribbean. It went over St. Lucia, just the north of Cuba. When it got to around about here, you can see the eyeball is just developing just through here. By the time it gets over to the Bahamas, it was a Category 4/5 system, and it ended up being almost stationary for about 36 hours. Now, unfortunately, that created a lot of devastation for the Bahamas, and then you can kind of see it moving northwards again, just through here. So this is actually a really cool site to actually show for students to understand that, the weather changes day by day. So for instance, when Dorian was over the Bahamas, it was extremely windy, lots of rain, devastating for a couple of days. But then within a few days that the storm had moved on, and it was back to probably quite nice sunny weather. So this is the difference between different weather fronts going through. Weather changes quite quickly. There's another video we can watch here. This is just from Australia, showing all the different cloud patterns which go over Australia. This is from 2010 all the way to 2016. As we go through here, you'll see there's lots of cyclones forming in the north. Well, not lots, but there's a few each year which form over the north. There's one just here, and there's another one just there. So again, this is a nice representation of what our atmosphere looks like day by day. And, weather changes quite frequently, especially down here in Melbourne where we live. And it's often noted that in Melbourne has 4 seasons in one day because the weather changes so frequently. But we'll get to Melbourne shortly. So again, just another image you can watch. The YouTube clip channel is just up here. So if you want to watch that in your own time, please go ahead. So let's actually try and explain the difference between weather and climate. So what do we mean by climate? And we can kind of look at that by using weather information. So here I've got Melbourne Olympic Park, here in Victoria, in Australia, and this is March 2020. This is the daily weather observations in Melbourne Olympic Park. Now, obviously there's 31 days here in March, and so we've got 31 lines of data, and there's a whole series of information, including the minimum and the maximum temperature, the amount of rain, wind, 9 a.m. and 3 p.m. conditions. Now, all of this information is available freely on the Bureau of Meteorology's website. It's an awesome area to collect data and use in your lessons. And in another lesson, I'll be showing you how we can actually manipulate this data in order to come out with different assessments and assignments for students. So that's coming up soon. Right, so let's look at Melbourne. So we have the 1st and 2nd of March of 2020. Now, notice that the maximum temperature on Sunday, the 1st of March, was 32.1 degrees. But the maximum temperature the following day was only 18.4 degrees. Now, this is what we mean by weather. Weather changes day by day. So, for instance, on the Sunday, we had a strong northerly flowing. And during summer and early autumn, especially in Victoria, when we get these strong northerlies coming through, it's dragging hot air down from the interior of Australia. And then obviously a front has gone through because the next day we have southerly winds blowing, and southerly winds obviously mean we get cooler temperatures here in the southern hemisphere. So this is showing you the 2 days over the first 2 days of March, and we have quite a wide range in temperatures. So the easy way to describe the difference between weather and climate is that weather is what is happening at very short timescales, usually over days, hours to days, whereas climate is how the atmosphere acts over longer periods of time. So a nice way to think of it is that climate is the sum of long periods of weather. Let's show what that means. I'm now going to take all of the information from Olympic Park, measured in March for the maximum temperature over a 5-year period. This is 2016 to 2020. Blue is 2016, red 2017, silver 2018, yellow 2019, and green 2020. You'll see down here on the x-axis, I've got the dates in March from the 1st to the 31st, and then I have the maximum temperature recorded in degrees Celsius. So if we look for 5 years worth of data, and we look on the 1st of March, now we'd already seen from the previous chart, remember I showed you that green, which is 2020, was 32 degrees in Melbourne. Well, if we look at the 2019 data, it's even warmer. It's about 37, 38 degrees. whereas back in 2018, the 1st of March was just above 20 degrees Celsius. So we can see there's a big range in temperatures on the 1st of March over 5 years. The changes in each of those is due to different weather patterns affecting Victoria. So probably this yellow and the blue and the green was when we had northerlies, possibly even the orange in 2017. But certainly I think that if we looked back on the 1st of March 2018, we would see that there was a southerly blowing in the Melbourne area. Okay, so what I can do now is I can take all the rest of that data. This, you remember we said that in 2020 it was hot on the 1st but cool on the 2nd. So I can take all of that 5 years of data. That ends up being 155 pieces of data because, of course, 5 years times 31 is 155. Now, what you can see is that March in the Southern Hemisphere is the first month of autumn. So you can see at the beginning of March, when we're just going from summer into autumn, it tends to be, these temperatures here look quite high. And as we start going through to the end of March, as we're going further and deeper into autumn, I think you'd probably agree that if we put a base trend line in here, you would see that the temperature is slowly decreasing through time in March. But of course, there's perturbations, there's changes every day, higher and lower, as different weather fronts affect Victoria. So we can take that 155 pieces of data. Notice that the warmest was back in 2016 when we had 38.9 degrees Celsius, and the coolest was in 2019 when we had 15.6 degrees Celsius. So rather than having a chart of the data, what we can do is now a histogram where we plot the frequency of temperature in March recorded in Melbourne. And this is kind of what it looks like. So we can build the histogram. So this means that between 15 and 16 degrees Celsius, there was one frequency, so one day. Between 23 and 24 degrees Celsius, this is this particular histogram bar here, and we had 13 days in that 5-day period, which was in that particular temperature range. We can actually put all of that information, and what we can do here looking at this is say, well, look, there's quite a large range of variation of the atmosphere here in Melbourne, but we can kind of see that around about here is the average temperature that we would kind of expect in Melbourne in March. Of course, there's a large range of variation, but what's important here is that we've got all of this weather data, but we want to try and make this into climatic data. So what we can do is we do some statistical work, which is literally just finding the standard deviation of all of these values. What we do is we still have that range of variation in the atmosphere, but now we have a value which is the typical state of the atmosphere in March in Melbourne based on that 5 years of data from 2016 to 2020. And that is the average temperature in March based over 5 years is 24.9 degrees Celsius. And that fits quite nicely because it's around about kind of in here. So this is how we refer to as climate. The climatic information in March in Melbourne is that we expect 24.9 degrees Celsius on average in Melbourne. That's climate. This is all weather. So let's delve a little bit closer into some information here, because I've put up it here, because again is the Bureau of Meteorology. It's a fantastic website for manipulating data and taking data out of their data sets, so we can use this to explain various phenomena to do with climate and weather. This is showing the average daily maximum temperature in March. And as would be expected in the north, it tends to be warmer because we're closer to the equator. And in the south, we're closer to the poles. And so it's cooler. So we have cooler temperatures here compared to what we see in the north. Now, let's just move into southeastern Australia a little bit. Now, we just worked out that in 2016 to 2020, over that 5-year period, the average temperature we'd expect in Melbourne in March is 24.9 degrees Celsius. And Melbourne's just about here. It's a little bit blurry, but it's kind of, it's kind of fits in just there. All right. So this is based on something very important. See this here? A lot, if not all, climate information you look at from government websites will always have this little proviso here, or this little box. It says it's based on a standard 30-year climatology from 1961 to 1990. But what does that mean? What it means is that if we go through time over temperature or rainfall or other climatic information or weather information, and we want to find out how the climate is changing, we kind of need a baseline in order for us to actually work out how things are changing through time. So the baseline is this 30-year period here, 1961 to 1990. What that means is we take 30 years of data, add it all together, divide it by 30, and that gives us an average. So it's exactly the same as what we did in Melbourne in March for 5 years, from 2016 to 2020. What the government and other organisations, weather and climate organisations, meteorology organisations do, is they then get an average, and then they can start comparing how temperature, rainfall and other climatic and weather information changes over longer time periods. So what this tells us is that in Melbourne, between 1961 to 1990, if we did exactly the same conversion as what we did before here, the average temperature in Melbourne over that 30-year period was 23.9 degrees Celsius. Now this is important because what we can do now is we can actually say, well, the temperature in March in Melbourne is actually increased by about 1 degree Celsius. Actually, it's not about, it's exactly 1 degree Celsius. So the climate has changed. In Melbourne, we've got 1 degree Celsius warmer, based on 1961 to 1990, is what we've received over that 5-year period here. Okay, so this is why it's important for us to take weather data, convert it into climate data in order for us to see how things are changing through time. Okay, so let's take Australia as a whole. We've got temperature information. We've actually got temperature information from before 1910 in many places, but the reason why here in Australia we use 1910 as our starting point when we're looking at climate change is because from 1910 onwards is when temperature recordings were standardised. So in other words, they used the same equipment all over Australia, rather than using different measurement techniques for temperature. So this is why we kind of start at 1910. This is giving us 110 years of data from 1910 to 2019. Now, again, look down here. This is important. The mean temperature anomalies are averaged over Australia as calculated from the 1961 to 1990 average. So what they've done here is they've taken all of the temperature data from Australia. They've worked out what the mean temperature is each year for the whole of Australia. They've then taken the 1961 to 1990 data, added it all together, divided by 30 to get a value. And that value is the nil value here. So this is the average over 30 years in Australia. And then whatever the temperature is, they call that 0. What we can then do is over the whole of Australia, we can start seeing, well, is a particular year warmer or cooler than that average between 1961 and 1990. Anything on here in blue is cooler, anything in red is warmer. Now, I think it's pretty clear that, and the other thing to point out here, this is empirical or directly measured evidence. This is directly measured data. I think it's pretty clear. You can actually see the temperature over the last 110 years has been increasing. In fact, in 2019, last year, the last full year of data available, in Australia, we were 1.52 degrees Celsius warmer than that 1961 to 1990 period. Okay. You'll also notice that there's this black line going through here, and this is kind of like a trend line. Usually with data, with trend lines, we just put a straight line through as a line of best fit. But when we want to make it a little bit more clearer what's happening over time, we use a moving average, which means that, so for instance, in 1920, I think that's 1920 just here, if we take 1920, if we take the previous 5 years and the following 5 years, add it to 1920 and divide it by 11, this is why we get a smoothed out curve. It's just more apparent. Think of it just like a trend line. So this is what this black line showing the 11-year moving average means. Of course, the last lot of data we got available for the trend lines, it stops early, is because, well, in order to do this year here, we need to have the previous 5 years and the next 5 years. We've only got 4 years in front of that. That's why the line stops here. When we get the 2020 data in at the end of 2020, early 2021, we can then move this line forward to wherever it goes to. But it is pretty obvious, I think, from this data here that the temperature, the mean temperature in Australia has been increasing, and it's about 1.52 degrees Celsius above the long-term anomaly recorded between 1961 and 1990. I know we spent a bit of time on there, but I think it's important for everyone to appreciate how we are able to clarify what is happening to our climate over time. So let's look at rainfall. We looked at temperature, but rainfall is actually quite interesting as well. This is the average rainfall in Australia, again, just down here. Notice it's based on a 30-year climatology from 1961 to 1990, and in a moment we'll look at the Melbourne data to show you how we calculate what that anomaly is. But I just want you to look at the whole of Australia here. You can see that it's wetter along the coastal areas, especially in Queensland, the Northern Territory. This is where we get the monsoon rainfalls, and occasionally we get cyclones. Tropical cyclones, and also down here the west coast of Tasmania is particularly wet as well, and that's because the prevailing wind in the southern parts of Australia come from kind of like the west or the southwest. So as soon as it hits these mountains we get lots of rainfall, and that will be another lesson plan we'll look at in the future called orographic rainfall, but more of that to come shortly. So let's look at Melbourne. So first of all, before we go to the data, I suppose the best thing to do is point out Melbourne is here, and it's kind of on the cusp of this lighter green and darker green, which is it's somewhere in here, around about 600 mils. But let's look at the exact measurement, because this is quite a large map of the whole of Australia, which means that you can't see the little variations over short distances down here. So let's look at Melbourne as an example. So what I've done here from the Bureau of Meteorology, I've taken all of the rainfall between 1961 and 1990. So again, we've got 30 years of data. I've added it all together, divided by 30, and I end up that the average rainfall in Melbourne is 638.84 millimetres based on this 30-year period. Now you may be wondering, why did we choose 1961 to 1990? Why don't we choose 1971 to 2000? Well, it's actually the date frame through here was chosen by the World Meteorological Organization a couple of decades ago in order to measure all this data. And the reason they did that was it's just it's sort of smack bang between where we start getting really good data being recorded, I suppose. I'm not actually sure exactly why they chose that 30-year period, but that's the period that we use. And we've kept that constant over the last 15, 20 years in order to compare and contrast what's been happening with that climate. So let's have a look at the annual rainfall in Melbourne. I've got all of this data here. All I can do is I can plot that year at the bottom on the x-axis, and on the y-axis I can plot the annual rainfall. So let's plot that. Hopefully, if it works. There we go. Right. So if we look here, 1961 we had just about 560 mils. What did we have? In 1961 we had 562 mils. Awesome. So all of this data here, it was a particularly dry year in 1967. 1967 only 332 mils, much lower than all the other data that we've got here for that 30-year period. So what we can do is then plot on the average rainfall per year. So what we can start doing then, if we just look at this 30-year period, we can say, okay, well 1961, 1962 was drier, 1963, 64 was wetter, it was a little bit drier in 65, a little bit wetter in 66, much drier in 67, etc., etc., etc. Okay, so this is why we want to find the mean, or we want to find the average over for a certain period of time, because we can start therefore comparing and contrasting different years. Okay, so what we can then do then is that we've actually got rainfall data all the way back from 1856 when Melbourne was first founded. So again, year at the bottom, and we have the annual rainfall at the side, and we can plot on all of the information for Melbourne. And there we have it at the end. What we can then do is actually plot on what our mean rainfall is in Melbourne over that 30-year period, which is just along here, which is 638 mils. Now this is interesting because when we looked at the temperature information for Australia, we could actually see there was a clear trend in increasing temperatures over that 110-year period. The problem we have here with rainfall is it's not so clear cut. It's not a very strong signal here telling us if we get more rainfall or less rainfall. So it's pretty, we go through between 1910 and about 1926, we had a couple of really wet years. It was a really dry year in 1967, which we know about. We really know about that one because we noticed that just here, 332.3 mils. In fact, that was the driest year on record here in Melbourne. But I think what you can probably notice is it does appear that in the last 20 years or so, maybe 25 years, we seem to be getting drier. We may be going through a drier trend here in Melbourne. There's certainly a lot more low rainfall recorded here. A couple of times we've had a lot wetter rainfall, which was up here in 2010, 2011. But the trend is difficult to see, but it does appear that we're kind of getting drier here in Melbourne. Of course, when we get more data over the next 10 years, we can just see if that pattern continues, but we can't really see into the future. We don't have a crystal ball. But what we can say is that the climate is changing in Melbourne towards a drier period. What's interesting is we can actually look at the whole of Australia, and again, we've got this all of this data here. This is years from 1900 to 2019, so this is 120 years worth of data. We've got rainfall here. This is the average mean rainfall in Australia. Now, what's really interesting here is that, again, there's peaks and troughs and peaks and troughs. It does appear since the 1970s that we appear to be having more extreme events occurring. So notice there's, again, the trend is not clear. It doesn't seem to be getting wetter or drier in the last, especially through this range here. But what I think you can see is that more extreme rainfall events, more extreme droughts, especially last year, which was the driest year on record here in Australia. We only had, on average, 277.63 mils of rain in Australia, averaged out over the entire continent. So, again, possibly more extreme events. Again, the data isn't very clear. It doesn't appear to be getting any wetter or drier over the whole of Australia, but certainly that idea of more extreme events seems to be coming through there. Okay. Again, directly measured evidence here, empirical data. This isn't modelled data. This is measured in the field by weathering stations. So I'm going to show you what one of these extreme weather events looks like. And we're going to look back on the 24th of March on 2019. Meteorologist Diana Eadie from the Bureau of Meteorology. We're going to use Diane's particular message here on YouTube for severe tropical cyclone Veronica. Now, this is severe tropical cyclone Veronica. It's coming into the Western Australian coastline here. It's about to impact. There was another tropical cyclone here, another severe tropical cyclone, which was Trevor, that the previous day had hit the Northern Territory borders, again causing lots of rainfall. So let's see what Diane Eadie says about severe tropical cyclone Veronica.
Hello from the Bureau of Meteorology. We're here with an update on severe tropical cyclone Veronica, expected to cross the Western Australia coast this afternoon or evening. Veronica is currently located off the Pilbara coast, just under 100 kilometres to the west of Port Hedland. It's a slow-moving Category 3 system, which continues to display a large eye with prolonged impacts expected for coastal areas. Winds and rain have already started to pick up. Legendre Island recorded a wind gust of 157 kilometres an hour earlier today, and we've seen 182 millimetres of rain around Port Hedland in the past 24 hours. A tropical cyclone warning is current from Mardi to Wallal Downs, extending inland to Marble Bar. Very destructive winds with gusts in excess of 165 kilometres an hour are possible near the centre of the cyclone as it approaches the coast. This includes Roebourne, Wickham and Point Sampson. A very dangerous storm tide is possible for parts of the Pilbara coast to the northeast of the cyclone. Tides are already running high and Veronica will force extra water onshore, so significant coastal inundation is possible. The biggest risk will be at high tide, which will occur around 1 p.m. today and around 1:30 a.m. tomorrow morning at Port Hedland. Rainfall totals in excess of 500 millimetres are possible with the passage of this system. This widespread heavy rain is expected to cause major flooding along the Pilbara coast.
Now I'm going to pause it there because a couple of things I want to point out. First of all, these numbers here are telling you about the intensity of the cyclone. Now, the cyclones, tropical cyclones, have a 5-scale standard that they use. So 5 is the highest and 1 is the lowest. So if we have a category 4, it means it's a particularly severe cyclone which is coming in. Now, you're probably wondering as well, what is a cyclone? Well, a cyclone and a hurricane and a typhoon are all exactly the same weather phenomena. The reason we use different names is because depending on the geographical setting you're in, you call these storms slightly different names. So, for instance, in Australia and in India and Pakistan, we refer to these as cyclones. If you live in the and also in the Southwest Pacific, we call them cyclones. In the Northern Pacific, we refer to them as typhoons, and in North America, they are in the Caribbean, they're referred to as hurricanes. So all the same kind of storms. These are pretty severe events. And what's actually interesting as well is notice how the cyclone is coming in and then it kind of does this weird 90-degree deflection. Well, let's have a look at that. Also notice, of course, that they were forecasting lots of rain near Port Hedland, this is the Pilbara coast here, and Port Hedland is right on the coast, and it's just probably about here. So they were expecting a lot of rain to fall. Right, so this is the track here of the cyclone, and if it's in orange and yellows, it basically means that this was when it was a severe category 4 or 5 storm. And you can see it basically came in and then it got deflected. Now, the reason it got deflected was quite interesting because severe tropical cyclone Trevor had just passed the Northern Territory border. Northern Territory coast just here. And so as that was moving inland, it started, and there was another low pressure system just here, it started to deflect the cyclone Veronica away. So instead of making its way inland, it did a little bump, it hit the coast, and then it moved sideways, all because of these low pressure systems just here. All right. So this is the cyclone coming in, severe tropical cyclone Veronica. You can see a beautiful eye wall in here, and this sort of came in here and then bumped away. So it didn't bump away because it hit the coast and it was deflected by the coast. It was deflected by these large systems which had just crossed over into the Northern Territory. All right, so let's look at Port Hedland. They were expecting a lot of rain there. And the actual rainfall, the average annual rainfall in Port Hedland, which is just here, I've got about 300 mils a year. That's based on looking just at this map. You can kind of see that it was probably just between this yellow and this greenish colour. There's probably just a bit of yellow up here, which means that it was somewhere between here. The actual amount recorded from the Bureau of Meteorology at their Port Hedland site is actually 291 mils per year. All right, again, based on that 30-year climatology. So between 1961 and 1990, an average of 291 millimetres of rain fell every year on Port Hedland. Sometimes it was wetter, sometimes it was dry, but this was the average amount. So 291 mils isn't a huge amount of rain. In fact, it's usually quite nice and beautiful up here on the Pilbara coast in northern Western Australia. When we actually look at the 7-day rainfall for Port Hedland, we already had one site. This is the, let me just show you here, the week ending 26th of March, showing the weekly rainfall which fell in Australia over that 7-day period. And you can see that some places, like up here, where Tropical Cyclone Trevor went, in fact, Tropical Cyclone Trevor came from here, went over the over far north Queensland, and then came into the Northern Territory. So that's why there's so much rain up here. And also there's a lot of rain around Port Hedland because of Cyclone Veronica. So that 7-day period over Port Hedland was actually 355.8 mils of rain, which was much more than what they get in 1 year. So this is what I'm just trying to get to you as well about this idea about climate versus weather. If you were a tourist and you were in Port Hedland towards the end of March in 2019 and you had 7 days there, you'd probably be thinking, wow, it's so wet and it's so windy and there's so much rain coming through, and this is a really wet part of the world and a really stormy part of the world. In actual fact, that's weather. You're experiencing weather there. Climate is that if you look at the climate, you'll notice it's only 291 mils of rain. And so the climate in Port Hedland is actually quite equitable, but it does get punctuated by these severe weather events. And this is one of those particular severe weather events, the severe tropical cyclone Veronica. So again, just really giving you an idea between weather and climate here. I just wanted to bring this up. This is actually from Twitter, from RA Road, and this is actually quite nice because it shows how climate is changing in Australia over time. And it's basing it on precipitation, total annual precipitation, versus the average annual daily mean temperature. So all of that information we saw earlier about rainfall and temperature over the whole of Australia each year, it's actually been plotted on a different type of graph. And this shows us when it's cooler and drier, cooler and wetter. This is hot and wet, and this is hot and dry. Now, what's interesting here is that you can actually see that the 20-year period between 2000 and 2019 is marked in red, and all of the years are actually hotter than the mean coming through here. All right. If you go back through time in 20-year periods, you can see that we tend to be plotting in 1910 to 1939, 1940 to 1959, those two 20-year periods, we tend to be more towards the cooler, whereas since then it's been getting warmer and warmer. Sometimes it's hot and dry, sometimes it's hot and wet, but this is just a nice graph plotting all of the climatic information for Australia since 1910 all the way through to 2019. So it's quite a cool image there. So why do we get those changes? So some years we've seen we get particularly wet areas, and some years it tends to be particularly dry. But why is that? And also, why is Australia's climate so changing so frequently? Why does Australia's weather change so frequently? It's kind of to do with the fact that we are an island, we're surrounded by ocean, and it kind of means that we end up with a lot of different weather phenomena can affect us. Some you may have heard of before, like El Nino and La Nina. These occur every 2 to 5 years. It swings between one to the other, then back again, and then back again. And it's kind of to do with sea surface temperatures off the coast of Queensland here, and also further along the Pacific towards the South American coast. So El Nino, La Nina is multi-decadal. We get it a couple of times every decade. Every year we get the monsoon, so this is a yearly event. Tropical cyclones, they come in every now and again, probably 2 or 3 per year over in this part of Australia, maybe 2 or 3 over in this part of Australia as well. But we also have some important ones like the Indian Ocean Dipole. And until last year, not many people had actually heard of this. It's kind of to do with the sea surface temperatures off Western Australia. If the temperatures tend to be warmer offshore, then it means that there's more chance for evaporation to occur, and we end up getting wetter periods over parts of Australia. If the temperatures tend to be cooler, we get less evaporation, and so therefore we tend to have dry conditions. Now, the Indian Ocean Dipole, and the same thing happens with El Nino and La Nina, but the Indian Ocean Dipole, of course, is based here over in the Indian Ocean, whereas El Nino and La Nina is based over in the Pacific Ocean. Now, we had a particularly dry year over much of Australia because we had a very strong Indian Ocean dipole event. That's broken down, which is over the last few months, which is why we started getting more and more wet weather over in eastern Australia. And luckily, the drought seems to have broken in many parts of eastern Australia. So all of these different large-scale atmospheric oscillations, they control our weather, and ultimately they control what happens climatically in Australia as well. So why do we care? I've explained the difference between climate and weather, but why ultimately do we care about our climate? Well, there's many reasons, but one of them in particular, and what I feel is a really important feature, is that our Earth can be classified terrestrially via different biomes. Okay, this is showing all the different biomes on Earth. A biome is an area on our Earth that can be classified according to the animals and the plants that live in it. Okay, so I've got the biome of tropical forest here. So we've got tropical forests here. Of course, we can get many different ecosystems within a tropical forest, as we can get many different ecosystems within a temperate forest as well. But this is kind of giving you just a broad idea of the different terrestrial biomes that occur on Earth, and these are based on climatic factors, especially temperature and rainfall. So some of these you've probably heard of before, like deserts. You've probably heard of forests, hopefully. We have temperate forests, we have boreal forests or tropical forests, depending on distance from the equator. Okay, so what's important here is that precipitation and temperature are probably the two most important variables that define where we have a particular biome. Okay, so if I look at precipitation here in centimetres, so we've got low rainfall, high rainfall, low temperatures, and high temperatures. Okay, as we change climate on Earth, we're going to start different areas of the Earth which are currently experiencing one type of biome may well change into another type of biome. Now that has really big implications for the animals and the flora and the fauna, so the animals and vegetation living there today. They're going to have to either adapt or they're going to have to move. I'm going to use the example here of tundra. Now tundra is frozen desert. Okay, we don't get, so tundra is large parts of tundra over places like Russia, Siberia, North America and Canada. If we start to increase the temperature, we're going to go from a tundra environment and then we're going to start going into a boreal forest. So we're going to go from one biome to another. All those ecosystems are going to be changing into other types of ecosystems. And especially when we start defrosting or thawing frozen ground, that's going to lead to a lot of greenhouse gases entering the atmosphere, which have already been frozen in the tundra, especially things like methane. So what does that mean? Well, this is some modelling by NASA, and what NASA looked at was what are the probability of one biome changing into another biome. Let's explain what that means. So for instance, if we go back here, if I increase temperature within the desert, it's not really going to change into anything else because there's nothing more than a desert it can change into. And that's what it's showing here. It's showing anything in purple has got a low probability of occurring by 2100. So we're not going to change from a desert into another biome like that, if that makes sense. But if we look at tundra, frozen wastelands over much of northern Europe and parts of southern Europe, there's an almost 100% chance of that occurring. It's just showing you that the whole ecological makeup of Earth, and in particular the biomes as well, are going to be changing with increasing climate change, and that should be enough to enact us to actually make changes to how our climate is changing. Right, so it's not just Australia where we get a warmer climate, it's a global one. This actually goes up to about 2012. I did try and find a more recent one of these, but the temperatures have been increasing, but it doesn't include all of the continents. So I just wanted to include this just to show that it is a global challenge that we actually face here. It's not just one particular part of the Earth. And I'll also just leave you with these two particular YouTube clips. The first one is this is showing all the different continents, and Australia's just here. This actual anomaly is based on 1951 to 1980, so it's slightly different, but it's same 30-year period. And what it's showing you is this is the null value or the average value. And as we start going, particularly into the 21st century, you can actually see that all around the Earth we are increasing our temperatures quite considerably above this background level of 0. So that's one YouTube clip, so it's just up here, and the other one I wanted to show you again. Both of these come from the Finnish Meteorological Organisation, using NASA data and using other data from other meteorological societies. Again, this is showing you all the different countries in the Earth, and it's showing you the temperature anomaly. Again, based on that 1951 to 1980 period, anything in red is warmer than that 1951 to 1980 average. Anything in blue is cooler, and as we can see, we are getting warmer. Right, and I'll leave it at that. Okay, so I'll just leave you a couple of things. This is I'm available on Instagram, where I do a lot of science communication. Any teachers, if you have any questions about this, please contact me. We have a multifaceted outreach program here at the Monash University. Brilliant Maps is available on Twitter and also on Instagram. They're pretty good for geographical information. Skeptical Science website. This is a very, very good site from an Australian-American team who basically do a lot of work on debunking climate change myths in order for people to understand how data is generated, and also just trying to look at some of the most common climate change myths. This is an awesome site. And I will leave it at there. So thank you very much for your time. As I say, if you want more information about the multifaceted outreach program we run here, especially in terms of physical geography, earth sciences and climate science, please let me know. Until the next time we meet, thanks very much for your time. Goodbye.